Hey guys, my name is Walid, and in part one we covered basically briefly four flip-flops, B flip-flop, T flip-flop, SR, and JK flip-flop. And we did one example using PN flip-flop. In this video we'll be working on more examples like our previous example, and let's begin. So in this question that I have, we're given two statements that are a p plus 1, which is equal to x, y naught plus x b, and b p plus 1, which is equal to x a plus x b naught, and then we have z equals a. And they tell us that this is our output. And we're trying to draw a logic diagram of the circuit, list the state table for the sequential circuit, and draw a corresponding state diagram. Okay? So we're doing three things in this case, given this. Alright, first thing that we notice right away looking at this is that we have two states. Okay? So 2 bits for the states. Alright? And we also have output. Okay? So before we do anything, since we have the equation, we can draw the logical circuit of it. So it's easiest to draw a logical circuit using D flip-flop. So right away, we know we're going to have D flip-flop, which gives us whatever we put in becomes our next state. So there are 2 states. We have 2 bits for state A and state B. So we're going to have 2 flip-flops. 2 D flip-flops, 1 for A and 1 for B. Okay? And both are controlled by a clock. Okay, and we have one input, which is X. Alright? So we got one input. So in our first one, and we also have Y. So we got Y. Okay? So in our first one, we know that it's X and Y naught. So we NAND it here, X and Y naught, or X or B. Okay? So we're gonna over this, anyways, X or B. We AND it and we put in OR gate, both of them, and that becomes our A. Okay? And for B, it's the same thing. We got X, so we take our X and A, and we take our A, okay, and then we have OR X or B naught. So again, we take X and we take B and NOT it, and put it in AND gate and OR gate, and put it in B. That's a circuit for these 2 equations, and we know our X equals A, right? I mean Z equals A, right? So the point is, looking at the equation, drawing the circuit becomes really easy. All right. Now we need to draw the table for it. But before we go to the table, so table requires following things, right? Like I mentioned in the previous video, we have to have our previous state. We need to have inputs, and we need to have output, or sorry, next state. And in this case, we have output, so we're going to have output. So this is, since we're using 2 bits, so our previous state is going to have 2 bits, and our input's going to have 2 bits. So 2 bits means 4 cases. So for 4 cases, we're going to have 4. For each case, we're going to have 4 cases of X and Y. So in total, it's going to be 16. Okay? So our next states again A and B, and we have Z. Notice over here, it says Z equals A, right? Which is equivalent to AT, right? So that means our previous state in that case. AT. It's equivalent to A. Just because it says A, it means the previous state. So 16 cases. So I'm going to have zeros. 1, 2, 3, 4, 6, 7, 8. here. For each of them, I'm going to have 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, and 1, and 1. And so we can see clearly, I'm going to just divide it up using the line. So let's do that, I think. Here, here, and now we got 16 cases, okay? Since it's easy, it's previous to our A, previous state. Since we have zeros over here and ones over here, I can simply, for Z, put that value in 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, and 1, 1, 1, and 1. Challenge is over here, right? And to put those in, we have our A and B over here, okay? What do we need to do? We need to look at A and B separately for our next state, which is equal, A is equal to this, and B is equal to this, okay? So in first case, first state, which is going to be, let's draw our state diagram over here, okay? At the same time, we know it's 0, 0, 0, 1, 1, 1, 1, 0, okay? And since we know that our output is consistent, we can put it right away in there. So it's for 0, 0, it's 0. For 0, 1, it's 0. For 1, 1, it's 1. And for 1, 0, it's 1. Right? So that's our state diagram. So let's look at it. Let's fill this up. We have to do it separately for A and B. In the first case, A equals 0, B equals 0. So we don't have A in the first case. So we do have B. So I'm going to put 0 over here. And X and Y values are changing. So let's do it. So X, so I'm going to use a different marker. So for X, it's 0. And for Y, it's 0. So since it's Y naught, we're going to put 1. Right? That gives us 0. Because X, 0 and 1, 0. Or 0 and 0, which is 0. So we get 0. Okay? So next, our X value stays the same. However, our Y value changes. So still 0. Okay? In next case, our X value is changing and Y becomes 0. So in this case, they both are 1 and this is 1. So 1 and 1 gives us 1 or 1, 0. We get 1. In next case, our Y is 1, so this becomes 0. We get 0 again. Right? Alright. Now our B is changing. So I'm going to erase this. Our B changes to 1. We get 1 down here. And then we have X equals 0, 0. So X equals 0. And this equals 1. Alright? So this gives us 0. Then we have 0, 1. Y becomes 0. We still get 0. Then X becomes 1. And we don't care about Y in this case because, you know, we have 1. So they're both going to be 1 regardless. Next case, our B is 0 again. However, our A is 1, but we don't have A in the equation. We don't care about that. And it's going to be the same case as before because it's the same situation as this. So we're going to put 0, 0, 1, 0. All right? And the last case is B equals 1 again. So this is going to be equal to that. 0, 0, 1, and 1. All right? So our state A, next state, is solved. Let's go to this state. All right? In first case, our A is 0. Over here, notice we care about both A and B. Right? So B is 0, but since it's B naught, it's going to be 1. So, and we don't care about Y in this case. So we only care about X. So when our X is 0, we're going to have 0 and 0. In first two cases, we're going to get 0. When our X is 1, in this case, we're going to get 1. Okay? So in our next case, where A equals 0 and B equals 1. So A equals 0, it stays the same. B equals 1. Since it's B naught, we're going to put 0. Doesn't matter, X becomes 1, notice, or 0. We're going to get 0 in either ways. So it's going to be 0, 0, 0, 0. Next case, our A equals 1 and B equals 0. So in both cases, they both are 1 because B is 0, so not it, so it becomes 1, A is 1. When X is 0, we're going to get 0. You can see that over here. Whenever you time 0 with 1, you get 0, so it's 0, 0. Whenever it's 1, 1, you're going to get 1, 1. Okay? And in our last case, our B equals 1, A equals 1, so we change B to 0, and A equals 1. Now, whenever our X is 0, we're going to get 0, so we put 0 in. And whenever it's 1, we're going to get 1 because of A down here, so we put 1. Here. We got a full table of our diagram that we wanted, and now we can finish the state diagram using that table. So you can see that each of them has 4 cases, right? So when my state is 0, right, I have 4 inputs, 0, 0. Next state, it stays over here, so I can just put it backwards, because it's 0, 0, it stays there. When it's 0, 1, it still stays there, so I can put 0, 1 over here. When it's 1, 0, it goes to 1, 1. Okay? So when it's 1, 0, it goes to 1, 1. And when it's 1, 1, it goes to 0, 1. So when it's 1, 1, it goes to 0, 1. In our second case, second state, right, when it's 0, 0, it goes back to 0, 0. I mean, this 0, 0, it goes back to state 0, 0. So we put that all down here. When it's 0, 1, it still goes back to 0, 0. So, and then when it's 1, 0, we go to 1, 0. And when it's 1, 1, it goes to 1, 0. We're done with our second state. Let's go to third state. When it's 0, 0, we go to 0, 0. When it's 0, 1, we go to 0, 0. When it's 1, 0, we go to 1, 1. And when it's 1, 1, we go to 0, 1. So it's 1, 1. So we go to 0, 1. So the last case is 1, 1 state. When it's 0, 0, we go to 0, 0. When it's 0, 1, we go to 0, 0. 0, 1 as well. And when it's 1, 0, we go to 1, 1. When it's 1, 0, we go back to 1, 1. And when it's 1, 1, we go to 1, 1. So that's your state diagram of this. Notice, by having equation and by getting this, we can go anywhere. So this is important for the circuit diagram, and this is important for the state diagram, and we can go backwards the similar way. Let's do more examples, then you'll see how it works. I'm going to erase this quickly. I'm going to do an example using a circuit that's given to us. We're given a full adder, which we know has 3 inputs, 2 inputs, which is X and Y in this case, and our previous carry, and then we get our sum and our carry. In this circuit, our carry goes to our D flip-flop, and we get a Q value, and that becomes this. Okay, this is controlled by clock, and we need to find everything else. This is a pretty easy question. Again, the first thing we need to draw is the table, and drawing table is very easy because we know we need our previous state. In this case, our previous state and the next state is represented by Q, which is 1 bit. We're going to have a Q. We're going to have our 2 inputs, X and Y. And as an output, we're going to have our sum. Actually, let's put carry first. So next state, our Q. So next state, input, and previous state. Right? And then we have our output, which is our sum. Okay? This is pretty easy to do because for each previous state, 0, 0, 0, 0, we have 4 possibilities, 0, 0, 0, 1, 1, 0, and 1, 1. 1, 1, 1, 1. So 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1. Okay? And we all can add. It's pretty simple. 0 plus 0 plus 0, we get 0 for next carry and 0 for sum. Then we have 1, 0 plus 0 plus this. Let me just put plus line in there so you can see. 0 plus this. We get 0 and our sum equals 1, right? Then we have 0 plus 1 plus 0, same thing, 0, 1. And then we have 0 plus 1 plus 1, which gives us 1, 0. So that means our next carry is 1 and our sum is 0. Okay? For the second state, I'm just going to put a line down here so you can see it easily. For second case, it's the opposite. So we have 1, 0, 0, 1 plus 0 plus 0. So what do we get? We get 1 for the sum and 0 for the carry. And then we have 1 plus 0 plus 1. In this case, it's going to be 1, 0. Because, 1, 1 gives us 1, 0. So this is our carry, this is our sum in this case. So we get, again, 1, 0. Next case is the same, 1, 0. Last case, sorry, this is 1, 0. So you get 1, 0, right? 1, 1. Yeah. So last case, we have 1 and 1 and so we get 1, 0, and then we have 1 more, so we get 1, 1. Okay? So both of them will be 1 and 1. So you got our table. From here, if we want to get the equation, that's pretty simple. And the state diagram is pretty simple. Because state diagram is actually very easy because we only have 1 bit. So that means we only have 2 states, right? This mark is not working properly. So 2 states. One state is 0 and one state is 1. Okay? For each state we have 4 possibilities and some output. But since output is changing, we have put it with our input. So let's look at it. Our first state, when it's 0, 0, we remain on the same state and our sum equals 0. So we remain on the same state at 0, 0 and our sum is 0. For 0, 1, we stay on the same state. For 0, 1, it's the same state and our sum equals 1. And then for 1, 0, it's the same thing. Remain on the same 1, 0. Remain on the same state and our output is 1, which is sum. For 1, 1, we go to the next state. State 1 for 1, 1, but our output is 0. For state 1, at 0, 0, we go back to the previous state, which is 0, but our sum is 1, so 0, 0, output is 1. For next 0, 1, we stay on the same state, and our output is 0. Same goes for 1, 0. Output is 0, but for 1, 1, we stay on the same state, however, our output is 1. So 1, 1, output equals 1. That's our state diagram. It was pretty straightforward from this point on. If we want to get the equation, we're going to have 2 equations. We're going to have equation for next state, which in this case is 1 bit only, so we need 1 k-map for that. And we need 1 k-map for our output. Okay? So let's do the output for next state, which is carry. And this is called carry. We have 3 bits representing that. We have Q, we have our X and Y value. So 0, 1. So 0, 0, 0, 1, 1, 1, 1, 0. And then we have 1 k-map for sum, and same thing. 3 bits. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Over here, for our next state, we have 1 at 0, 1, 1. So 1 at 0, 1, 1. So we're going to put 1 down here. Then 1 at 1, 0, 1, 1, 0, 1, 1 here. 1, 1, 0, 1, 1, 0, 1 here, and 1, 1, 1 here. This gives us, we're going to have like 3 groups over here. So 1, 2, and 3 groups. And we can write down the equation using those groups. So our carry equation for this circuit is, let me just change the pen. Is equals to, so let's look at this one. This circuit cancels the Q, so we get X and Y. Or this one, we get Q, and we cancel out because 0 and 1, X is changing, we get Y. And in this one, x gets, x is not changing, but y is changing, so we get y. So x, we get x, right? And for the last case, for the sum, we're going to do the same thing. We're going to fill in the values. So sum is at 0, 0, 1, so 0, 0, 1 down here. And then it's at 0, 1, 0, so 0, 1, 0 down here. And it's 1, 0, 0 down here, and 1, 1, 1 down here. Okay, so we cannot make any group. This is a special kind of K-map that just simply implies our sum, in this case, is equal to, sorry, I forgot to put Q and XY, Q, XY. So this is simply equals to Q, our previous state, X or our next, X or Y, okay? So now we get everything for this particular circuit. Again, we got this right, we could make state diagram, and we can get our equations from this point on, okay? This was pretty straightforward. Let's do one more example before we end this video. And in our next video, we're going to use flip-flops to represent, we're going to use time to show how flip-flop works using time clock. Let's do one more example. So, unlike before, we're going to use state diagram, and we're going to go backwards, okay? So, our state diagram looks like this. In this case, we have 2 bits representing our each state, 0, 0, 1, 1, 0, 1, 1, 0. So 0, 0, if we have input of 0, we stay there, but if we have input of 1, we go to 1, 1. From here, if we have input of 0, we stay there, but if we have input of 1, we go to the next state. And same thing over here. So at 1, 0, if we have input of 0, we stay on the same state, but if we have input of 1, we go back to 0, 0. Okay? So now, if we're going to draw a table for that, we're going to have our previous state. We're going to have our input. We're going to have our next state. Since our state is represented by 2 bits, I'm going to call them AB. And our input equals X, our next state equals AB. Okay? So, in case of state 0, 0, we're going to have 2 cases of X, because X either can be 1 or 0. When it's 0, we stay at 0, 0. But when it's 1, this becomes 1, 1. Okay? Then, 0, 0, 0, 1, at this state, when we have 0, it remains on the same state, 0, 1, but it's 1, it becomes 1, 0. Then at 1, 0, when it's 0, it remains on the same state, 1, 0. However, when it's 0, when it's 1, it goes back to 0, 0. Last state, 1, 1. When it's 0, it stays on the same state. When it's 1, it goes to 0, 1. That's our table. Okay? Let's divide it. We can see it easily. We're going to have something like that. Ooh, a little messy. Here. And here. Okay? We got that table. From here, if we need the equation for this circuit, we know our next state is represented by 2 bits, so we need 2 K-maps for each bit. So A, T plus 1, K-map for that. 3 bits, we're using 3 bits, 1 for